Welcome back to P3. This should be the last video for the section. Let's dive right in. In this section, we're going to talk about scientific notation. It's usually done in the same section as integer exponents because it's a direct application. We won't use this much in our class, but you'll see it a lot if you ever take a chemistry class. Scientific notation is just a notation used to represent very large or very small numbers. So like if you wanted to talk about the size of an atom or a molecule in units that we're more familiar with, like meters, then you'd want to use scientific notation to get an idea of just exactly how many meters or centimeters it would be long. Now, realistically, for a lot of things, you would use really tiny units, like nanometers. But sometimes you want to talk about everything in the same unit, and you'll have very small amounts and very large amounts. Probably the most commonly seen number that has scientific notation in it is Avogadro's number. If you've ever seen that, 6.022 times 10 to the 23rd, I believe. But let's get through the theory in this section. So scientific notation is used to abbreviate very long numbers, whether they are very large or very small. So here's an example. I abbreviated 123 million, 6 zeros, as 1.23 times 10 to the 8th. And that is equal, if you multiply that out on the calculator, literally take 1.23 times 10 to the 8th, you will get that. And this number, 0.00000, let's see, that is 489 zeros, is 7.61 times 10 to the negative 10th. And again, if you multiplied that out on your calculator, you would get this number. Although, probably this one on your calculator, it would just give you 7.61 e negative 10, like this. 7.61, and it would just say e negative 10. That's actually your calculator giving you scientific notation. In the calculator, e negative 10 means times 10 to the negative 10. It's just an abbreviated notation. How it works? Well, you can see here, they're just taking the decimal point from wherever it is and putting it right here or here. It's to the right of the first non-zero number from left to right. The book actually says the first number always has to be between 0 and 10, and that's a good way of expressing it. But I always say it's just to the right of the first non-zero digit, reading left to right. Well, once you know it has to go there, you just count how many places you have to move it. Decimal point was here. So it moved 1, 2, 3, sorry about that, 4, 5, 6, 7, 8. It moved 8 places to end up right there. Well, that's why it is 1.23 times 10 to the 8th. If you move the decimal place to the left, you get positive exponents on the 10. And if you move it the other way, 4, 8, 10, you get negative exponents on the 10. That's really all there is to it as far as converting to the notation. There's a little bit more complexity when you're actually dealing with doing operations with it, addition and subtraction, multiplication and division. We'll probably only see multiplication and division in our course. Addition and subtraction isn't that much harder. You can just look it up yourself if you want. For exercises, I'm literally just going to read some problems out of the book and we'll do them there. This is on page 23 of your book. So I'm going to do a problem from 43 and 44, we're supposed to write the number indicated in scientific notation. Easy enough. So this first number, how many places do I need to move the decimal point? 3, 6, 9, 12, just 12. So my final number is going to be 5.9 times 10 to the 12th. Sometimes the problem will also tell you it wants you to round the number. If this had told me, say, to round to the ones position, I would end up with 6 times 10 to the 12th. But it didn't say anything about rounding, so just watch for that in the homework. Part B of the same problem, very small number, diameter of electron, very small number of centimeters. I always find the small numbers harder because you don't have the commas as an easy guide. We'll see if we can count. That's 4, another 4 is right here, 8, another 4 is right here, 12, then 13. So this would be 4, you can do 4.0 if you want, but times 10 to the 13th. Almost every semester a student asks me if this is a typo. It is not. A billion billion. Well, a billion is a billion is 1,000,000,000,000, or more easily 10 to the 9th. So if you have a billion billions, a billion billion would be 10 to the 9th times 10 to the 9th. So that would be 10 to the 18th. And if you have 33 times 10 to the 18th, that's almost in scientific notation, but the decimal point isn't in the right place. The decimal point is right here, and it needs to be in between the 3 and the 3. So if you move it one more place, and you end up with 3.3, now it is times 10 to the 19th. And we're good. Let's go down to a word problem. This is exercise 55. It says the average ocean depth is 3.7 times 10 to the 3rd meters. The area of the oceans is 3.6 times 10 to the 14th. That stands for square meters if you're not familiar with it. What is the total volume of the ocean in liters? 1 cubic meter contains 1,000 liters. Well, first off, let's find cubic meters. If you're familiar with really any shape, it doesn't matter what the top looks like. If you're trying to find the volume, if you know the area of the top, you could even take a weird shape like this. Oh, now I've got it. Honestly, that's pretty good for me. Even if you got a weird shape like this, as long as you know the area and the depth, the area of this weird shape times the depth of the shape is just going to be the volume. All you need to do is take the area times the volume. In fact, if you're familiar with the volume of a box, that is length times width times depth. That's the area of a side of the box times the depth. Yeah, it's true in general. If you want to find the volume of a shaped object, you just find the area of a cross-section and multiply by the depth. Now, if it doesn't have a constant depth, then that's a problem, and you've got to work that out. But all of these have a constant depth. So all we've got to do is multiply these two numbers, the 3.7 times 10 to the third and the 3.6 times 10 to the 14th. So we do that, 3.7 times 10 to the third times 3.6 times 10 to the 14th and because of the commutativity of multiplication, it doesn't really matter which parts I multiply. I can reorder, so I'm going to multiply the 10 to the third times the 10 to the 14th. That'll get me 10 to the 17th. And then 3.6 times 3.7 I'll do in the calculator. Clear 3.6 times, I should just use the numpad on this, it's easier. But just so you can see my key presses, times 3.7 is 13.32. So I have 13.32 times 10 to the 17th. Now note a couple things here. First off, this is in cubic meters, and I am going to have to convert to liters. Also, this is not in scientific notation. Scientific notation, I need the decimal point here. So I move it one more place, 1.332. Now, if you're not sure quite whether you're going to be subtracting or adding 1 to this number, well, if you think about it, to move the decimal place 1 to the left, you have to divide by 10. But I want the number to still be the same, so if I divide by 10, I've also got to multiply times 10. So I just divide this part by the 10 and multiply this part by the 10, and I end up with times 10 to the 18th. That's generally what I do if I'm not quite sure which way I'm going with it. So it's 1.332 times 10 to the 18th. Now, need to convert to liters. Every cubic meter has 1,000 liters in it. So I'm going to take my number of cubic meters, which is 1.332 times 10 to the 18th, and I'm going to multiply that times 1,000. But since 1,000 is just 10 to the third, 10 to the third times 10 to the 18th, I can just add their exponents. 10 to the 21st, and that will be my answer. 1.332 times 10 to the 21st. Don't know why I'm having such trouble drawing that. Try again. Okay. That's a multiplication of numbers in scientific notation. If you were doing a division, like for example, 54. The speed of light is about 186,000 miles per second. Use the information in exercise 44A. The information in the 44A says the distance to sun is 93 million miles. So let's convert that to scientific notation real fast. 93 million, that's 6 zeros, so 6 decimal places, then one more, would be 9.3 times 10 to the 7th. 186,000 miles per second would be 1.86 times 10 to the 5 to the 5th. How long does it take for a light ray from the sun to reach the earth? So distance equals rate times time. We want to solve for time. Time equals distance divided by rate. Our distance is 9.3 times 10 to the 7th. Our rate is 1.86 times 10 to the 5th. 9.3 divided by 1.86. Probably going to have to round this one. 9.3 divided by 1.86. Oh, that goes in evenly. It's 5 times 10 to the 7 minus 5 is 2. That's such a small number relatively. There's no reason to express it in scientific notation, because that's just 5 times 100, or 500 seconds. I believe I put on a very similar problem in the homework. Pay attention to what they asked for in that, because I believe they asked for minutes, not seconds. If you want to convert this to minutes, you'd have to divide by 60. I think that'll be the last exercise for the section. I hope you enjoyed the lecture. Join me next time for a discussion of P4, when we start bringing other types of numbers than just integers into the exponents. We'll look at roots, we'll look at rational numbers in the exponents. See you then.